Good morning, everyone. Let's start. In the previous class, I introduced Huffman codes as an alternative to the Shannon codes. Right? So we're trying to design optimal in the sense of minimizing the expected length prefix-free codes. And we saw that Huffman codes, at least for certain examples, performs better than the Shannon code. The Shannon code was bad because for certain probabilities, unless the source was dyadic, the Shannon codes in general are not optimal. You can get shorter code words for at least certain symbols. So we looked at Huffman codes using a few examples and recall that the Huffman coding procedure is to sort of merge the two. So you iteratively merge two symbols with the least probabilities to get a super symbol. So now you have Huffman codes over m symbols. You reduce it to designing a Huffman code for m-1 symbols and m-2 symbols and so on. So you keep iteratively reducing the size of your alphabet until you get just two symbols or one symbol. Right? That is something that we know how to handle. Okay, and remember, in every step we are trying to merge the two symbols of the least probability. Now, this sort of merging principle, you can do it in different ways, but Huffman codes is this specific technique where you are merging least probability symbols. And in general, of course, I think someone pointed out that, well, we could also try to partition symbols into two subsets. In every stage, you try to partition into two symbols, having roughly equal probability, right? So instead of a bottom-up approach, you could try to use a top-down approach, but in general, that is not going to be optimal. Okay. Okay. So now we'll see that Huffman codes are in fact optimal in the sense that among all prefix-free codes, the Huffman codes achieve the minimum expected length for the given source. The Huffman code is not the unique code which achieves the minimum expected length. There could be other codes achieving the same expected length, but no prefix-free code can achieve a smaller expected length than the Huffman codes. All right. Any questions? All right. So recall that for any prefix-free code, the minimum expected length is always bounded between entropy and entropy plus 1 bits. We've shown that every prefix-free code must satisfy this particular inequality, right? And that is because, well, we give a proof in terms of using the KL divergence. We showed that the expected length minus h of x can be written as not exactly a KL divergence, but using the log sum inequality, we can show that this quantity is always greater than or equal to 0, and therefore the minimum expected length is always greater than or equal to entropy. Okay, and also the minimum expected length must be less than or equal to entropy plus 1 bits, because we know that the Shannon code achieves an expected length of less than or equal to h of x plus 1 bits. So the minimum expected length can only be less than or equal to that of the Shannon code. It may be the same as the Shannon code, but certainly the minimum expected length cannot be larger than that. Right? So this is something that we know in general. So the claim is that Huffman codes also achieve the same bounds. So it's going to be within these two bounds, but now the lower bound is not just entropy, but it is the expected length of the Huffman code. That is L star of Px. Okay, so what we want to show is that if LH of Px for a given source Px, if LH of Px is the expected length for any Huffman code, then the minimum expected length is equal to LH of Px. So that is what we will try to prove today. All right. So here's a general claim. So given any optimal prefix-free code, we can construct a prefix-free code which satisfies these properties. So there could be different optimal prefix-free codes. Remember that in the previous class we saw 2 to 3 different examples of Huffman codes, different Huffman codes for the same source. Depending on how you merge symbols, uh, there is a choice between 2 or 3 different Huffman codes. All of them achieve the same expected length, right? So you can have 2 different codes achieving the same expected length. So there could be multiple optimal prefix codes. Now the claim is that there is always an optimal prefix code which satisfies the following 3 properties. The first property is that if you look at any 2 symbols, A and B, where the probability of A is greater than probability of B, then the optimal code gives a length L of A and L of B such that L of A is less than or equal to L of B. So obviously that is obvious, because if the probability is larger, then the optimal code should assign a shorter code word length to that particular symbol. All right. Because if not, you can always exchange the 2 code words and that will give you a smaller expected length. Okay, so if you take any 2 symbols A and B with P of A greater than P of B, then L of A should be less than or equal to L of B for an optimal prefix code. Okay, so hopefully this is clear. Any questions? Okay. The second property that we look for in among the class of optimal codes is the following. So if you look at any 2 symbols, so if you look at all possible symbols having the least probability, assume that P of A, P of B, P of C, maybe there are 3 different symbols, all having the least probability. Okay, all of the symbols have probability greater than these 3. So all of these 3 are equal, and this is the minimum probability. So maybe 0.001 or something. Okay. So the claim is that now if you look at the lengths of these 3 code words, L of A, L of B, L of C, the code word lengths for these particular symbols, then it must be the case that either, well, 2 of them should be equal, L of B, and the third one should be strictly smaller. Okay, or all of them can have the same length. So only the following can happen. L of B is equal to L of C, or whatever, 2 symbols. So maybe L of B is equal to L of C and L of A is strictly smaller. So 2 of them are going to be equal, and the third one is either equal to the other 2 or it is strictly smaller. Okay, that's the only thing which can happen. It is not possible. The following cannot happen, that maybe one is strictly larger than L of B and L of C is also larger than L of A. So this cannot happen. Okay, is the statement clear?
Sir,
Yes.
you said any 2 can have same length.
Uh-huh. So among symbols of the least probability, I'm only focusing on symbols having the least probability. Okay.
Okay, among those with least probability which are equal only that
Yeah,
you
yeah.
consider.
So you look at all possible symbols having the least probability. If there is one symbol, then fine, there's nothing to argue about. Uh, but 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 you look at least two symbols with the least probability. So okay, so this also covers the case where you take any two symbols, P of A, the symbol with the least probability. If there's one symbol of the least probability, fine. If So you look at least two symbols, you order all possible symbols in order of probability. So let's assume that x1, let me call it, right? So let's look at P of A is greater than or equal to P of B, greater than or equal to P of C, greater than or equal to P of D, and so on. Okay, so let's assume that this is the case. So A is the symbol with the least probability, B is the one with second least probability, C third least, D fourth least, and so on. Okay, and let us assume that the length of A is greater than or equal to the length of B, which is greater than or equal to length of C, and so on by property 1. So it's an optimal code. So obviously this chain of inequalities should be satisfied. Without loss of generality, we can assume that this is the case. Okay. Now the claim is that no matter what happens, L of A is equal to L of B. So L of A cannot be strictly larger than L of B in this case.
Sir, could you explain why do you say so? Why should we impose this equality constraint?
Why should we impose, sorry, what?
Why are you imposing this equality constraint? It can still be greater than or equal to, right?
Which equality constraint?
LA equal to LB.
L of A, I'll come to that. So this is what, so in terms of if the code is optimal, then this necessarily must be true. And the reason is the following. So think about the code word lengths in terms of the code word tree. Okay.
Sir, this
Yes.
is for the the top two symbols with the highest probability.
With the least probability.
Oh, okay. Oh, sorry.
So
Yeah.
remember, P of A is less than or equal to P of B, which is less than or equal to P of C, and so on. So you take two symbols of the least probability, or correspondingly the two longest code words. Then the claim is that the two longest code words are equal. The longest lengths, there cannot be only one code word with the longest length. There are at least two of them. Okay. At least is the statement clear? We'll see why that has to happen, but is there any question regarding the statement? So if I order the lengths in the decreasing order of lengths, then and I look at the two longest lengths, L of A and L of B, then these two have to be equal. That is the claim. Okay. So let's construct the general code word tree for the prefix free code. Okay. What will be the depth of this tree? In terms of these L of A, L of B, L of C, and so on.
So the longest code word.
Exactly. So in this case, what is it?
L of A.
It will be L of A. Okay. Okay. So the depth is equal to L of A, right? And what am I saying? So suppose that this is not the case. Maybe L of A is not equal to L of B. Okay. If not, then so if L of A is strictly larger than L of B, then it means that there is no code word. There's only one code word which has this length L of A. All other code words have lengths strictly less than L of A. Okay. So if you look at the code word tree, you look at all possible code words at the basically you look at all possible leaves of this code word tree. Only one of them is a code word. Okay, maybe this one is a code word, and none of the other leaves correspond to code words. Okay, so this is not a code word. This is not a code word. None of these are code words. That is the claim. Right. So L of A is strictly larger than L of B. So none of the green ones are code words. Only the blue one is a valid code word. Okay. And the claim is that, well, the assumption is that this is an optimal prefix-free code. Right. What I'm saying is that you can now reduce the length of the code of this particular code word without changing any of the other code words. If this is the case, if you look at this particular tree and you know that this blue point, this blue leaf is a code word, then I can simply reduce the length of this code word without changing the others, and it will still be a prefix-free code.
Because the parent, it can't have.
Exactly. So the parent is not a code word, and its sibling, that is this one over here, this is not a code word, right? This is not a code word. So I can, instead of taking this as the code word, I can simply take this as the code word, right? So this means that I can choose this as the code word instead of this one, and therefore now I've reduced the length. The expected length obviously will decrease, right? We can construct a prefix code with L prime, so a new code with L prime of A equal to whatever, it's at least less than or equal to L of A minus 1 and L prime of B. All the other lengths are going to be the same. And so on. Right? And therefore this cannot be optimal. All right, and therefore it must be the case that for any prefix-free, if it's an optimal prefix-free code, then there must be at least two code words of the longest length. And these two should obviously correspond to symbols of the two least probabilities, right? Just because of assumption one, that if you have the smaller probabilities correspond to longer code word lengths. Okay, is this clear? Okay. The third point, yeah. The third property is that in an optimal code, the two longest code words, now remember there are at least two code words with the longest length. The two longest code words will differ only, you can always find two longest code words which differ only in the last bit. So basically if this is a code word, right? So you look at all code words at the maximum depth. Correct? So you look at all code words at the maximum depth, basically the code words which correspond to leaves in this code word tree. You can always pick a pair which differ only in the last bit. So it is not possible that these two are the only longest code words. Do you agree?
The code word sibling would be
Sorry, can you repeat?
no, so like how are we taking two code words at the end in a sense?
Correct. So the claim is that this cannot happen. What
Oh.
I've drawn over here, this cannot happen.
It would
Because
be
if,
a neighboring leaf of the.
correct, so the two longest code words are going to be neighbors. So if this is a longest code word, then its sibling should also be a code word. Otherwise, of course, you can always shorten this particular code word. All right. Now, there could be code words which are not siblings, right? So for example, if these four are valid code words, right? Maybe these four are code words. All right. So this code word and this code word do not differ only in the last bit. All right. But for every longest code word, you can find its sibling, which is also a valid code word. Right? So you can find two longest code words which differ only in the last bit. Is that clear?
Yes, sir.
Any questions?
Sir, are you proving Huffman codes is one of the optimal codes, or Huffman code is only optimal code which is possible?
No, of course. We can't say that it is the only optimal code. There could be other codes which are also optimal. Because obviously, even the Huffman code itself is not necessarily unique, right? There could be two or more possible Huffman codes for a given source.
So, but we have even told that we don't have any other coding which can perform better than
Correct.
coding.
Correct. But there could be a code which is not obtained by the Huffman code procedure, but it achieves the same expected length as the Huffman code. The claim is that you can't do better than a Huffman code, but it doesn't mean that you can't do the same as a Huffman code.
Okay.
So right now, these three properties that we are seeing, right? So property 1, 2, 3, these have to be satisfied by every prefix-free code. Right? Every optimal prefix-free code. It could be obtained using the Huffman coding procedure. It could be obtained by some other procedure. Doesn't matter. But if the code is optimal and prefix-free, then these three properties have to be satisfied. Okay, these are general properties of any optimal prefix code. So in particular, Huffman codes satisfy these properties, but there could be non-Huffman codes which also satisfy these properties and they're optimal. They achieve the minimum expected length for the source. Okay. So right now I just proved a general property of optimal prefix-free codes. I've not yet shown that Huffman codes are optimal, right? I'm introducing these properties because I want to show that among all codes, among all prefix-free codes, Huffman codes achieve the minimum expected length. Okay. And these are properties that every prefix code should satisfy. And I will be using this in the proof in order to prove that Huffman codes are optimal. Okay. So let us look at a general source, okay, on M symbols. Okay, so the source has M symbols, and we'll assume that the probabilities of the symbols are as follows. So P superscript M denotes the probability mass function on the N symbol. So the superscript indicates the size of the alphabet, and the subscript essentially denotes that this is the probability corresponding to the ith symbol. Okay, so just for convenience, we will assume that P1 is greater than or equal to P2, which is greater than or equal to P3, and so on, greater than or equal to Pn. Okay, and we will look at an optimal prefix-free code for this particular source. So consider any optimal code for Pn. Okay, let us call it CM star. Okay, so some procedure using some algorithm, you maybe get an optimal prefix code, and I'll call it CM star. Now I'm going to make some assumptions here. Well, assumptions in the sense that I'll assume that the two longest code words suppose that symbols M and M-1 have the longest code word lengths, and these code words differ only in the last bit. Right, so basically, if you look at the code word tree, then this is what it looks like. So this would be the code word for, maybe this is the code word for symbol M, this is the code word for symbol M-1. Now some of these other leaves could also be valid code words. Maybe the optimal code for this particular source looks something like this. That is fine. Okay, this could potentially be the optimal prefix code, but whatever. So the only assumption, the only thing that I'm saying is that M and M-1 are the two least probable symbols. They could have the same probability or different probabilities, doesn't matter. But these are the two least probable symbols, and they correspond to the two longest code words, and which differ only in the last bit. Okay. That's my assumption on CM star. Okay, so this is my CM star. So for every n, I'm going to assume that this is going to happen. I can always construct a code such that this happens, right? So I'm only looking at a general n. Okay, is that clear?
Yes.
Okay. Now what we're going to do is, so what is the goal? So let us also consider, let CH be the Huffman code. Maybe let me denote it slightly differently. Let's say CMH is the Huffman code. Is the Huffman code for the probability mass function on M symbols. All right. So what do you want to show? Want to show that the expected length of the Huffman code on these M symbols is equal to the expected length of the optimal code, CM star. Okay, so this is what we want to show. And this holds for all possible probability mass functions for all M. M equal to 1, 2, 3, and so on. Right? So we'll prove this via induction. Proof via induction. Okay, so let's look at this. Let's start with M equal to 2. Okay, what is the optimal code for two symbols? What is
0 and 1.
C2 star? Exactly, it is 0 and 1, right? No matter what the sources, no matter what the probabilities are, as long as they're strictly positive, right? As long as P0, whatever, okay, P1 is greater than 0 and P2 is greater than 0, the optimal code is this, right? And what is the Huffman code?
Zero, one.
This is also going to be 0, 1 because the Huffman code is obtained by merging these two symbols and then assigning bits 0 and 1 to these two, right? So I'm not claiming that the Huffman code is equal to the optimal code anywhere over here, right? The only claim is about the expected lengths. Okay, and clearly the expected, so what is the expected length of the optimal code?
One bit.
It's 1 bit. Good. Right? And the Huffman code is also the same thing. Okay, so no matter what the probability mass function is, as long as M is equal to 2, we've shown that the expected length of the Huffman code is equal to the expected length of the optimal code, of any optimal code. Okay? Now let's do the induction step. Suppose that Huffman code are optimal for all distributions on M-1 symbols. As long as the alphabet is less than or equal to M-1, we know that the Huffman code is optimal. What we're going to show is that for every distribution on M symbols, Huffman codes are also optimal. Okay. So now what we are going to do is look at the first step is now consider the Huffman code Okay, so even before that, let's look at the so we have the following PMF. All right, so this is P1, P2, up to Pn. Right, and we assume that these probabilities are in decreasing order, or at least non-increasing order. So let me consider a new PMF on m-1 symbols. Okay, so it is P1, P2, up to, so in this case, Pm-1, Pm, Pm-2, and the last probability is Pm-1 plus Pn. Okay, so this is a new probability mass function on m-1 symbols. Okay, it's a valid probability mass function since the sum of the probabilities is equal to 1. It's still equal to 1. So essentially, I have merged these two symbols to create a new symbol. Okay, this is some source. Okay, and the probabilities may not necessarily be in the decreasing order, but that doesn't matter. Okay, so this is the original source. This is sort of the new source. Okay. Now let us look at the Huffman code. The Huffman code on m-1 symbols for Pm-1. Okay, and let ch m be the Huffman code for Pm, the original source. Right. So what can you say about these two? What is the relationship between these two Huffman codes? So what are going to be the code words for the first n-2 symbols for this Huffman code and this Huffman code?
So what was the question again?
Sorry?
What was the question again?
Okay, the question is, now I want to understand what is the relationship between these two Huffman codes. Remember that the first Huffman code, CHM-1, sorry, maybe I got my notation a little wrong. So CM-1 H and CM H. So this is the Huffman code. So this second thing, this is the Huffman code for the original source. Okay, and CM-1H is the Huffman code for the merged source, where I'm merging the last two least probability symbols to create a super symbol. And then on this source, I'm going to construct a Huffman code. So what can you say, what is the relationship between these two?
Up to up to m-2, the code lengths will be same.
Exactly, the code words will also be the same, right?
Code words will be same length, and when we have this merged probability,
Correct.
so there it's like we that will be like a leaf kind of thing. There won't be further splitting in M, where we have P M minus 1 and PM separately, that would split.
Correct. So if you look at the code word tree for PM, if you look at the code word tree for PM, maybe this is M and this is M minus 1 and this is M. This is for PM. For PM minus 1, the rest of the code word tree remains the same, but these two code words are replaced by this single code word, the green code word, right? So because you're just merging these two symbols to create a new super symbol, the probability of the super symbol is PM minus 1 plus PM. And so the Huffman tree for this particular source is going to be the rest of it. You just remove these two and then you replace it with this new code word. Correct? So because the Huffman code is sort of this iterative process where the Huffman code for the merged symbol, the original source is obtained by taking the longest code word and assigning two new code words, right? Is this clear? So all the other code words for the first M minus 2 symbols, the code words for PM and PM minus 1 are going to be the same. Of course, there are different ways to construct Huffman codes, but there's one way to construct a Huffman code such that, at least for one of the Huffman codes, the code words for the first M minus 2 symbols are the same for both sources. Only for this particular symbol, this is going to be the code word, whereas for the other source, for the last two symbols, these are just the children of this particular code word. All right? Does everybody agree?
Yes, sir.
Okay. So now let's look at the expected lengths. All right. The expected. What can you say about expected length of? The notation is L of CMH versus, I want to express this in terms of LCM minus 1H. So for the first M minus 2 code words equal to 1 to M minus 2 PI LI plus, it's going to be the same, the two are going to be the same, but for the last code word, it's going to be something different. So PM minus 1 L M minus 1 plus PM LM M minus 1H (1 to M minus 2). For the first code words, first M minus 2 code words, it is the same, plus what can you say about the last symbol? The last symbol has probability PM minus 1 plus PM. And what can you say about the length assigned to the last symbol?
1 less than the
Correct.
previous
So
one.
exactly. So these two are going to be the same. LM minus 1 and LM are basically the same. So it is going to be LM minus 1 minus 1. All right. So what is it in terms of LM? So it is summation I equal to 1 to M minus 2 PI LI plus PM minus 1 LM minus 1 plus PM LM minus Pm minus 1 minus Pm. Okay, so it is L of the expected code word length for the Huffman code on M symbols minus of Pm minus 1 plus Pm. You agree?
Sir,
Yes.
this summation PILI plus PM minus 1 LM minus 1 plus PM LM minus 1 or LM?
Which one? Okay, so LM is equal to LM minus 1, right?
Okay.
Because the two longest code words have the same length. Right? So LM is equal to LM minus 1. Okay, so this was for the Huffman code. Now let us look at the optimal code. So let us now consider the optimal code, and let us say that this is the expected length L of C star M. Right, so this is summation I equal to 1 to L equal to M. Let's say Pi Li star. Okay. Fine. So this is going to be the optimal code. Right. Now in the optimal code, let us say that I just merge the two symbols. Okay, the two least probability symbols. So I look at the optimal code. It could be anything. It could be a Huffman code. It may not be a Huffman code. Doesn't matter. But I'm going to look at the two symbols with the least probability, and I'm going to merge them. Right. So I'm going to merge them to get this new code word. So I originally had a code for PM. I'm going to get a new code for PM minus 1. I'm not claiming that the new code for PM minus 1 is optimal or anything, but then if I merge these two symbols to get a new code word, then the resulting code on M minus 1 symbols is a valid prefix free code. Do you agree?
So can you repeat that statement?
So you have the code words. So let's say code word for symbol 1, code word for symbol 2, and so on, code word for symbol M minus 1 and code word for symbol M. All right. So these correspond to symbols with probability P1, P2, Pm minus 1, and Pm. Now from this code, and so this is an optimal code. So this is some optimal code. It achieves the minimum expected length. It's a prefix-free code. I'm going to construct a new prefix-free code, which may or may not be optimal. So the new code on P1, P2 up to Pm minus 2, Pm minus 1 plus Pm. So it's a new code on M minus 1 symbols. Okay. It's a new code on M minus 1 symbols. So, and the code words are obtained as follows. For the first M minus 2 symbols, I'm going to keep them as it is. C of M minus 2. For this last symbol, it is going to be something different. So let me call it C tilde of M minus 1. Okay, and this is obtained by just removing the last bit of these two. So remember, these two are the longest code words, and the assumption is that they differ only in the last bit. Right? Basically, they are siblings in the code word tree. I'm just removing this, and for this for this particular symbol, I'm representing it, I'm assigning it this particular code word. So the code words for these two, let us assume that these two were the code words for PM-1 and PM. For PM-1 plus PM, I'm assigning it's their parent as the code word. Okay, that is all that I'm doing. So the resulting code, so this code, the claim is that this is a prefix code. Okay, it is a prefix code. It may or may not be optimal, doesn't matter. Okay, I'm starting with some optimal prefix free code, looking at the code word tree, taking the longest code words, which differ only in the last bit. And for this new source on M-1 symbols, I'm designing a new code where the first M-2 code words are the same. The M-1 code word is just the parent of these two particular code words. Okay, this is some prefix code. Okay, is this construction clear?
Yes, sir.
Yes.
Okay, great. All right. So now let us see the relationship between the expected lengths of these two code words. Right, so we had L of C star M, which is summation I equal to 1 to M Pi Li star. Now let us call the new code Cm-1. What can you say about this expected length? For the first M-2 symbols, it is the same, Pi Li. What about the last two symbols? Or there's only one symbol left. M-1 plus PM. What is the length going to be? What is the length for this in terms of the lengths for these two?
LM minus
LM-1.
Correct. So it is LM-1 minus 1. Right? And so we get essentially the same thing, right? So this is summation, well, it's not LM-1 star minus 1. I equal to 1 to M Pi Li star minus PM-1 minus PM. Right? So L of Cm-1 is equal to L star of Cm-1. Sorry, I guess L of Cm-1 star minus of PM-1 plus PM. So the expected length of this new code, of the shortened code, is equal to the length of the optimal code on M symbols minus PM-1 plus PM. Okay, so let me call this equation number 2. We had a similar equation for similar relationship between the Huffman codes for M-1 and M symbols, right? Let me call this equation 1. So the expected length of the Huffman code on M-1 symbols is equal to the expected length for the Huffman code on M symbols minus PM-1 plus PM. So it's the same thing, except that these two are changed. So let me take these two equations, and we're almost done. So I have this and I have this. Okay, so let me just subtract the two. I get L of Cm minus 1h minus L of Cm minus 1 is equal to L of Cm h minus L of Cm star. Okay. So I just subtract the second equation from the first. Now we've seen that, so both of these are expected lengths for codes on m-1 symbols. These two are expected lengths for codes on m symbols, right? What can you say about the left-hand side? We know that that Huffman codes are optimal for m-1 symbols, and this is some other code. So what can you say about the left-hand side?
Negative.
Yeah, so it's whatever, it's less than or equal to 0, right? So this quantity is less than or equal to 0 because this is the minimum expected length among all possible codes on m-1 symbols. So this quantity is less than or equal to 0. Therefore, this quantity should also be less than or equal to 0 because we have an equality. But what does that mean? So 0 is greater than or equal to L of CMH minus L of Cm star, or M star is greater than or equal to L of. So the Huffman code, the expected length of the Huffman code is going to be less than or equal to the minimum possible expected length, which just mean that this is an equality. Right? So among all possible codes on M symbols, Huffman codes achieves the minimum expected length. All right. Any questions? We'll stop here at this point. It seems a little bit, it may seem a little bit complicated, but go through the proof once again and you'll be able to follow it. There's nothing too complicated. It's just in one case you're extending the code, in the other case you're shortening the optimal code, and in the other case you're extending the Huffman code from m-1 to m symbols, and you're basically comparing the lengths. And since Huffman codes are optimal for all sources of on m-1 symbols, and you're comparing it with the optimal code on m symbols, you just the induction step works.
Sir?
Yes.
It's not like correlated to the proof, but this when we're combining the probabilities, can we interpret it like in when we're applying it somewhere? For example, I have 4 letters A, B,
Okay.
C, and D in my alphabet.
Okay.
So it's like C and D have the least probability, and they have the highest length.
Okay. So these two, of course, we're assuming that these two are the least probabilities, they have the highest length, and that they differ only in the last bit.
Okay, sir. So, yeah. So when we combine the probability,
Okay.
it's like CD together
Correct.
is getting one
Correct.
probability or like one same
Correct.
code. So this combining probabilities can be used when like when we are sending these symbols. Like A, B, and all, they're like quite frequent. C and D are like less probable, and
Correct.
if C and D always occur together, then we can
What do you mean by occur together?
so in the sense, it's like when I'm sending a sequence,
Okay.
in case my sequence, like in my file in that sequence, if D is always followed by C.
Okay, so it's not an IID sequence.
Okay. Yes, sir. So I thought it's like for C and D together when we're assigning a probability or a
Not really.
you can
Not
take it
really.
that way.
No, no, no. So you can, one way to interpret these codes is basically as a sequence of yes or no questions, right? You want to know what is the minimum yes or no questions in order to identify which of the symbols has occurred. It's either A or B or C or D, right?
Okay, sir. So
maybe this is
this combining probability, what is the significance, sir?
correct. So let's assume that this is the code word tree. Okay. Now, can you devise a sequence of yes or no questions which gets you to this? So you want to know whether it is this or it is this set, right? So what is the yes or no question you would ask to know whether you want to go down the tree left or down the tree right?
Sir, question means like code length?
No, just a sequence of questions which can be answered with yes or no. So suppose that I know
It's
what
like
the actual symbol is, okay? And you have to ask me a sequence of yes or no questions to find out whether it is A, B, C, or D.
so the left branch would be yes.
No. So what is the question you would ask? So you right now you don't know. Okay. Suppose I have one of these symbols in my mind. Okay.
Is it B, C, or D?
Okay. Is X B, C, or D? C or D. Now, if I say yes, then you know that it's going to be one of these. If it is no, then you know that it is A and you can stop. Correct?
Yes, sir.
Okay. So similarly, now suppose the answer is yes. Then what would be your next question?
Does X belong to C, comma D?
So C comma D, right? Now, if I say no, then you know that it is B. If I say yes, then you have to ask one more question, right?
Okay, sir.
So each bit corresponds to the answer of one particular question, right? So this would be a 0, this would be a 1, this would be a 0, this would be a 1, this would be a 0, this would be a 1. In general, as long as you have any code word tree, so basically it corresponds to a partitioning, right? A binary partitioning. So if this is a code word, if this is A, this is maybe B, this is C, this is D, and this is E. Your first question would be, is it A or B? If yes, then you go left. If no, then you go right. And then you would ask the question, is it C or D? Then if yes, then you would go left, otherwise you would go right. So essentially the length of the code corresponds to the number of yes or no questions you have to ask in order to reach that particular node.
Okay.
Right? So that's one way of interpreting it.
So the combining probability is like just like to, as you
Exactly.
said, which side to move for decision making.
Yeah, you combine, you don't care about which symbol it is. So suppose that on the new source, you don't care whether it is C or D. Okay, as long as you know if it is C or D, you're happy. Right? This is just the subset, C or D. Maybe at some point you just want to know whether it is C or D. You don't care about whether it is which one of the two it is. Then it corresponds to this new source. So the source has 4 symbols, A, B, E, and a new symbol which represents either C or D.
Okay, sir. Got it. Thank you.
And anyway, this merging technique was sort of just a proof technique, nothing else, because our ultimate goal was to show that Huffman codes achieve minimum expected length. So it's just a trick that we played. Right? Any other questions? Okay, so if not, we'll meet in the next class. So see you then.